opportunity to present this material to people who know a lot about symbolic algorithms and have a lot of experience with computer algebra, probably more than me, so I hope that I can get some good feedback here. This was the, this talk is based on the PhD dissertation of my former PhD student Brian Miller and subsequent paper on the integration of algebraic functions computing the logarithmic part. So the dissertation was done at Texas Tech University, defended in 2012. This work, since there are people here who have been talking about resultants and things that are involved in this work, this work started when I was teaching a course on Grosvenor basis, and when I was teaching the resultant, my student mentioned that he was reading the book of Bronstein, Symbolic Integration, and he mentioned that the resultant was used to compute integrals symbolically. So I asked him to give a talk about that, to give a seminar talk. So he talked about that, and I asked him some questions about that. So this work started from there, and he generalized some results in the transcendental case when you have transcendental integrals, but those were really not that interesting. The really interesting case was the one when the integral involves algebraic functions, which remains still very challenging. So I am going to talk about a procedure that he found, he came up with building on Coward's work, Manuel Coward's work. So I'm just going to tell you what the whole thing is about. I'm just going to briefly talk about the procedure for the sake of time, but in the paper he provides a procedure to compute the logarithmic part of an integral of an algebraic function. It finds closed form solutions that have been difficult to compute by other means, and he's able to fully justify it using techniques of Grosvenor basis, differential algebra, and algebraic geometry. So we start with this example, motivational example. So if you want to find an antiderivative for this function, and you feed it to Mathematica, you get this output. It says no result found in terms of standard mathematical functions. And you feed it to Maple, and it returns the same thing. It does nothing. Axiom returns an error. Brian Miller's procedure gives you the correct antiderivative for that. So which you can check by differentiation. Right? So it's interesting that it works for several situations where the standard methods do not solve, and the computer algebra systems can work it out. So this problem concerns integration in finite terms. So let K be a differential field and F a differential field extension. An element theta in F is said to be elementary over K if it is one of the following: a logarithm over K, and that means that the derivative of theta is dt over t for some t in K, an exponential over K, which means that d theta over theta is the derivative of some t in K, or algebraic over k. Everybody knows that algebraic is if it is the root of some polynomial with coefficients in k. And we say that f has an elementary integral over k if there exists a g elementary over k such that its derivative is equal to f. So an example of an elementary extension is k of x, y, z, where the derivative of x is equal to 1, the derivative of y is 1 over x, and the derivative of z is z. So y is logarithmic over q of x, and z is exponential over q of xy. Q of xy, z is an elementary extension of q of x. So this is a classical example. There is so the main result here that gives the tools to compute the integrals is this Liouville's theorem that says that basically that if a function has an integral in terms of elementary functions, then it has to have something that looks like the partial fractional decomposition that we know from calculus. So if E is a differential field with constant field C, and F is an element of E, let L be an elementary extension of E with constant field C as well. If the equation G prime equal F has a solution G in L, then there exists W, U1, U2, and to UN in E, and constants C1 to Cn in C, such that F is W prime plus the sum of Ci and the logarithmic derivatives of the Ui's. Of course, the above expression implies that F is the integral of F is W plus Ci, and the summation of Ci log of Ui. So some remarks here. The element, I was supposed to be doing page by page, so this is going to look a little bit awkward. So the element W is called the integral part, and the sum of the Ci log of Ui is called the logarithmic part. So algorithms to isolate W prime have been developed by Traeger and Bronstein. So that we are not interested in doing that. That has been done. Traeger and Bronstein, when they are computing when they are isolating the W prime, they also their algorithms also gives out the remainder of the function, the remaining part of the integral as a fraction b of theta y over b of theta, where the denominator is normal with respect to the derivation d, and that means that the greatest common divisor of the derivative of b and v is 1. Miller assumes this condition in his work, so he is not worried about computing the, or rather he uses the Traeger's and Bronstein's procedures to get this part, goes from there. So we assume that K is a field of characteristic 0 and theta is transcendental over K. We denote by y bar the expression in the integrand that is algebraic over K of theta, for example, square root of y minus 1, something like that. And we assume that it has minimal polynomial f of theta 1. We also assume, that, as I said before, that the integrand is in the form u of theta y bar u of theta. So we're trying to find this partial fraction of the composition for E of theta y bar over V of theta. So we're in other words, trying to find the functions ui and the coefficients ci that gives you this expression if they exist, because it's quite possible that the function may not be integrable in terms of elementary functions. So what do we know about these CIs and UIs? Well, Traeger and Bronstein show that the CIs are roots of the polynomial Z given by the resultant in theta of the resultant in y of U of theta y minus Z V prime theta F of theta y V of theta. And so, as I said, this was the generating element of this work, because my student had read this on Bronstein's book, and he noticed, and he brought that to our attention when I was teaching the course. So, following a heuristic algorithm given by Cauer, in this paper, Integration of Algebraic Functions, a simple heuristic for finding the logarithmic part, he considers the idea of U of theta minus Z V prime of theta F of theta y and V of theta. So he considers this ideal to find the CIs and the UIs. And we have some facts about this ideal. The ideal is zero-dimensional. It contains univariate polynomial Z, of which the Zi in this expression are roots. So we can compute these CIs, if we are lucky, by doing some primary decomposition that I'm going to talk about in a minute, and then finding the minimal element of a Grobner basis for this ideals, and then computing the roots of these minimal elements with the CI. So if we take the primary decomposition of I, then for all primes containing I, P is the radical of Q sub L for some L between 1 and M. This is just a standard commutative algebra. We take all the primes that contain I. These are finitely many because I is zero-dimensional. Partition them according to the following criteria. Two of those primes are going to be in the same partition if they have the same univariate polynomial in Z. So for then for I, for L between 1 and R, we let H sub L be the intersection for the primes and the Lth partition. H sub L is radical, and the use of I are in the HL. So these are facts that are proved in the paper. So the thing goes as follows. Compute a Grobner basis for H sub L. We are looking for U sub I in that Grobner basis such that the variety of Rz and F of theta y intersected with the variety of U sub I z theta y is the variety of the Grobner basis, where Rz is the univariate polynomial in Z of H sub L. In other words, we're looking for a U sub I such that the ideal generated by Rz F and U sub I is the ideal generated by the Grobler basis. So I'm going back now to the original example. I have been very skimpy with the details of the algorithm in the interest of time. If anyone is interested, I have the paper, and I really would like to talk to people about this and see what they can tell me, especially people who have experience with symbolic solution of differential equations and such. I'm sure can tell me something good. So back to our original example, let's see how all of this works. So our integrand here is 3x t2 plus 3y squared minus x t2 minus 1 plus divided by 24xy squared times t1 plus t2 minus y. And I have denoted by t1 the ln of x and t2 of x. So we have that the irreducible polynomial is of t1 plus t2 is y cubed minus t1 plus t2. So we have that. So we apply this procedure. We get h1 is a deal of az minus 1 t2 minus y plus t1 y squared minus 1, and then we see that for the element y squared minus 1, we have a to z minus 1 f y squared minus 1 is equal to h1. So the univariate polynomial in h1 is az minus 1. So our c1 here is 1/8. Hence, the 1/8 log of y squared minus 1 is a contribution to the integral. And we'll look at h2, and then this is going to be the ideal of 24z minus 1 t1 plus t2. And of course, remember this h2 would take them as the intersection of the primes in the in the second partition, according to the criterion that they have the same univariate z polynomial. And then for the element t1 plus t2, we have this condition, and the univariate polynomial in z is 24z minus 1. So we get that the residue here is 1/24. So we get this contribution to the integral. And well, there are some criteria. There's a criterion where to stop, and in this case, we just verify that putting it all together, and we get the integral. So that's how it works for this example. So there are so very nice things. So it has been tested on several examples where Mathematica, Maple, Axiom, and other computer algebra systems fail. So it's definitely improving the existing algorithms. All the procedures have been justified because this work was inspired by this heuristic paper of Cowers that gave solutions in many cases, but in many cases it was not the correct solution, and in other cases he got it correctly, but he didn't know why. So the procedure was, I mean, he didn't know how to justify the results. So he might since made a good effort to prove this. The paper is still being improved. But the two main questions remain to be answered. One is the procedure complete? Is it correct? Because we don't know when the procedure stops, if it is because there is no really an elementary integral, or if it is that we're not completing it correctly. So and the other is it complete. So we do not. I have been trying to isolate cases where I could address one of those, but I just have not been able to find some cases where I can, even for those small situations, say that. So if anyone here has any ideas or wants to say something about that, I'll be very happy to.
Thank you very much. Any questions, comments?
Just a couple of, so your constant field, did it need to be algebraically closed?
Yes.
And the second thing is, those examples where your method works and it doesn't work in Maple, Mathematica, or Axiom, I mean, do you sort of know how you would have constructed the examples sort of backwards at some level, right?
Right.
So it's at some level, do you understand sort of where the Axiom and Maple and Mathematica are lacking? I mean, where is it that you could sort of find the examples?
Well, we were just trying to come up with weird things that.
So what type of weird things? What was the type of weirdness that wouldn't give answers in Axiom, for example? Because Axiom is, I think, Traeger and Bronstein implemented that in Axiom.
Well, I think it was just luck. That we didn't have any real guide to find those examples. I think if I had a guide to find those examples, I could probably just have a guide to. So it was, yes.
If I understand correctly, this procedure is applied to this particular example, right? Have you tried other examples not constructed but naturally arise from, say, those old integral table or something, and then apply that procedure and check the results?
Oh yeah.
You have, okay.
Actually, there's very few intervals in integral tables. That are almost none.
So your completeness statement, what you would like to have is that it decides integrability of an arbitrary elementary function?
Yes.
That's the claim. Okay.
Maybe on the first example you showed, Maple and the other subs are confused because we are mixing two different fractions. And in some way, he cannot split the denominators. If you can show the first example.
Okay.
The denominator is a product of two very different expressions. And at least by hand, one could split the fraction into as a sum of two fractions. That's just the very first example.
Well, it's the only one, so.
Okay, sorry. Yeah.
Okay.
And I guess that you could split that into fractions, and maybe you could try Maple and the other sub on each fraction to see if that works. See? Like, maybe
I split up the two fractions.
Oh, I see what you're saying.
It would be like doing the splitting a fraction in elementary partial fraction, but on very complicated expressions.
Yeah.
And to see if that makes the integration work. That could be a hint also.
Making more difficult.
I see. Yeah, that's it.
I don't think Maple does that. Maple takes expressions like this and sort of tries to convert them into sort of their extended extended field, and then I think it actually sort of then separates it, but can't get the answer.
But maybe he tries to rename some expressions, and the log x plus exponential is in both parts of the. It happened with different powers and the fractional powers. Maybe that's where Maple got confused. So it's not so easy to transform that into a fraction. And,
Have you talked to Barry Treasurer about this? He's here at the conference.
Oh, is he? Oh, yeah, no, I haven't. Is he here?
He's here, not in the room, but.
Oh, okay, well,
you
yeah,
should talk to him about
Yes.
it. Yes.
Yes, if somebody could find it.
We can point you to Barry.
Yes, I'd be very happy to talk to him, yeah.
And you're going to talk at 3:30?
3:30, okay.
And your procedure, does it use factorization in some way?
The procedure uses factorization in some ways. Factorization of what? Of polynomials? Yes.
Yes, it does. And over what fields do you need factorization?
Over the reals?
Just the fields.
Yes.
Any more questions? More questions? More comments? Well, thank you very much.